Okay, we have here on the board another integral from the UNSW Integration Bee 2023. This was round 2, problem 15. We have the integral from 0 to 1 of the 20th root of 1 minus x to the 23rd minus the 23rd root of 1 minus x to the 20th dx. Okay, I thought this one was really interesting, and I noticed a similarity right away to a problem I did not too long ago from the Berkeley Integration Bee. Now, notice we have the situation where we have this minus sign here, and it could be a plus sign, and it'd be a similar situation. And that tells me we can actually break this into two integrals, right? And integrate these separately. So I think typically in a case like this where you're adding and subtracting two things within an integral, they kind of want you to, or they're hinting that we could actually find some relationship between these two things that's going to actually make this easier rather than making it like two integrals. So the next thing I wanted to do for this is what I did in the Berkeley Integration Bee, which was try to see if possibly these two things are inverses of each other. So let's just start with this first piece over here. We can call this f of x. So what I'm going to do to check the inverse on this is I'm going to actually set this whole thing equal to y, and we'll write that out. And then all I want to do is just try to solve for x. So what I'll do first is take the 20th power on both sides. So we're going to end up with y to the 20th equals 1 minus x to the 23rd. And then just rearranging, we'll get x 23rd alone. And so we can do this and subtract y to the 20th on both sides. And we're going to have 1 minus y to the 20th. And then I can take the 23rd root on both sides of these. And what you notice we end up with is, well, just x equals the 23rd root of 1 minus y to the 20th. And then what you'll notice is if you just take a look at this, and if you were to swap the x and the y, this is going to be exactly that value right there. So what that's going to tell us is that these two things are inverses. And so I can write this one here. I can write this as f inverse of x. So next, now that we've established that these two are inverses, I want to check the endpoints in order to get a rough graph. And so first what I'll do is we'll just deal with this first one. So let's look at f of 1. If you plug a 1 in here, well, this is going to become 0. So our value of f of 1 is going to be just 0. And then we'll look at our other endpoint, f of 0. We plug this in. Well, 1 minus 0 is going to be 1. It doesn't matter what the root is. So this is actually just going to be 1. Now, the exact same thing is actually going to happen on the inverse when we look at 1. It's the same kind of thing where you plug a 1 in here, you get 0. And then if you plug a 0 in here, you'll notice that you're going to get 1. So let's just take a quick look at the graphs of these things and see what we have. Okay, now we have this very rough graph over here to the right. And it's arbitrary what I chose to be the inverse and what I chose to be f of x because I couldn't really draw this accurately. But let's just say that our inverse function I have here in red and our regular f of x value is going to be in black. In reality, if you look at these graphs, because of the high power, the graph actually comes out and it's almost like a square because it comes all the way out to like the 1-1 point right here. Now, because these are inverses, the exact graphs are not really important because we have these endpoints here. So we know that we're going from 1 to 0 in this way. But the really important thing, because these are inverses, is there are reflections on this y equal x line right here, this dotted line. And because they're reflected on this y equal x line, if you just were to flip either of these, you would just get the other function. And you kind of see here how maybe the red function's got a little more area in this region because it's a little higher here. But then it has less area in this region because it's below the curve here. But really the point is, because these are reflections, if you just reflected it within this region from 1 to 0, these are actually going to have the same area. So from this, we know if we were to break this into two integrals, they both have the same value, but we're subtracting them. So subtracting the same exact area is just going to give us an answer of 0 for this. If you happen to see that previous video from the Berkeley Integration Bee where I mentioned that this was done in 2 seconds, this is really similar, where this is something you could actually do. As soon as you recognize this inverse is within this region, you could jump right to a solution of 0. I'll provide a link to that other video. I thought it was kind of interesting. It's a little different situation because I think we were adding, I think the bounds were different, so it's definitely not the same problem, but the same idea. So that's it. We'll stop it there. Thanks everyone for watching today. Have a great day.